All right, welcome physical science students. Today I am going to go over the study guide so that you can see whether or not you got the answers correct. And for the first part of the test, or the first part of the study guide, you're going to see definitions. And so these are things that you just need to know what they are. And the first one here is title. I don't think there's much to say about a title. It is something, though, that takes this form, how the, and then you put your independent variable, how your independent variable affects your dependent variable, whatever that is. Okay, you don't put in the actual words independent variable or dependent variable. You put in what the independent variable is, what the dependent variable is. All right, the next one, we have the hypothesis, and this is again your prediction for what will happen in the lab. And this is something where you're trying to be specific, and you're saying if you change something about the independent variable, then something about the dependent variable will change in a certain way. You don't want to be vague on this, but kind of the main thing is, remember, you want this to be an if-then statement. If you do something, then something else specifically will happen. All right, your independent variable, this is what the experimenter, or you, if you're the one who's doing the experiment, this is what the experimenter changes. In the example of taking basketball shots from different distances, I, the experimenter, am choosing to do it from different distances. So that the different distances are my independent variable. The dependent variable, that's the variable that changes because of what the experimenter changes. And it's also the thing that you measure. So what changes because of a change in the independent variable. But I think the easiest way to remember is it's what you measure. All right, constants. These are the opposite of variables, okay? Constants don't change. And remember, in a lab, almost everything, every material or every part of the environment around that experiment doesn't change. The only things that can change are the independent variable and the dependent variable, and you can only have one of each of these, but you can have a lot of constants. All right, so if I'm shooting a basketball at the outside hoop, I want to make sure I'm using the same ball. I'm shooting at the same hoop. I'm doing it at the same time of day because the sun's in the same place and I have the same weather and I'm shooting with the same force every time and I'm the one shooting. So there are just lots of things that stay the same. We call all of those things constants. And then we contrast that with what the control group is. So when I'm doing an experiment, I'm testing one group and I'm leaving another group alone. So this is the group of, I guess you could say, test subjects, where you don't change anything about what's going on. Not every experiment has a control group, but again, you do this in order to prove that your independent variable is the thing that's causing the changes. The experimental group, this is the group of test subjects. Okay, so the people or the things that you're doing a test on, in which you do make changes. All right, so again, let's say I'm going to make some cookies and I want to know, if I change the amount of flour, how will that change how high the cookies rise? And then I make one batch of cookies where I don't do anything different than I normally do. And so that's my control group. And then for the other cookies, I start adding flour or using less flour. They're the experimental group. When we record our data, we've got a couple different kinds. We have quantitative data, so this means you can measure it with numbers. So you can say how long, how much mass, how much time did it take. That's quantitative. Qualitative, this is more of a subjective thing. So like, if I said, what music do teenagers who are 14 and 15-year-old, like the best? Or what do I think, which flavor of pop do I like the best? I'm making judgment calls there. I'm saying, this one tastes better than that. That would be qualitative. There aren't numbers. That measure. I could create like a rating scale, but usually you're just comparing things to each other. So if I said I'm going to drink 5 kinds of pop and I'm going to rank them in order of what I like better, that would be, again, qualitative data. That's also sometimes just a little subjective. All right, next question here. When do you use a bar graph and when do you use a line graph? Use a bar graph when your independent variables, I'll put a little S there, independent variables are not related. They are separate, different things. The example that we did in class with a bar graph where you had to make one was the kinds of food that were imported from Brazil. You had shellfish, beef and veal, oranges, coffee, I think tomatoes, plus a few other ones. But again, none of them have anything to do with each other. Coffee and oranges are just completely separate things. They can't be connected. A line graph, on the other hand, this is where your independent variables are just an increasing number of things. Okay, so most of the time when we talk about line graphs, our x-axis is time. Time just goes from 0 seconds to 1 to 2 to 3 to 4 to 5. It's a continuous progression of time. So that's when you would use a line graph. All right, in a data table, what goes in the first column, the independent variable or the dependent variable? All right, so if I'm going to make a data table, my first column is where the independent variable goes, and that could be, whatever it is that I'm changing. But independent variable goes in the first column. And then if I only have one, if I only do one trial of something, my dependent variable would go in the next column. But if I do multiple trials, I would have a number of columns that are all dependent variable. Even my average is an average of the dependent variables. So this would be trial 1, trial 2, trial 3, and then the average. But all of those are the dependent variables, but independent variable goes right here. All right, so then I said, let's practice. Nate decides he wants to get to know how much time. Let me start over. Nate decides he wants to know how the time it takes water to freeze is changed by adding antifreeze. He gets 5 5-gallon buckets of water. He does nothing to the first bucket. He adds 1 tablespoon of antifreeze to the second bucket, 2 to the third, 3 to the fourth, and 4 to the fifth. He sets them outside on a day when the temperature was minus 20 degrees Celsius. He then recorded the time it took for the water in each bucket to freeze. For bucket 1, the water freezes in 55 minutes. For bucket 2, the water freezes in 110 minutes. Bucket 2, the water freezes in 200, that should be bucket 3. The water freezes in 220 minutes. Bucket 4, the water freezes in 440 minutes. And for bucket 5, the bucket freezes in 880 minutes. And then I must have gotten thrown off track, so we're just going to skip this last one. Okay, so then the questions are, what is the independent variable? So what is it that Nate is changing every time in this lab? Well, let's just draw a quick little picture here of what's going on. So he's got 5 buckets, right? And there's water in each bucket. And in this one, he puts 0 tablespoons of antifreeze. Here he puts 1 tablespoon, 2 tablespoons, 3 tablespoons, and 4 tablespoons. All right, and then he sets them outside on a cold day and waits for them to freeze, and then he's timing them. So what's different about each one? The number of tablespoons of antifreeze. So that's the independent variable. Amount of antifreeze. All right, so then what's the dependent variable? What's he measuring? He's waiting for them to freeze, and he's timing that. So that's the time to freeze. What are some constants? Well, the outside temp. Probably the amount of water. Size of bucket. What else is there? I think that's it, probably brand of antifreeze. Okay, so those are all things that have to stay the same because we want to make sure that it's the amount of antifreeze that makes a difference. The question is there a control group? And yes, this bucket right here, this is just plain water. There is no antifreeze in that. So that's the control group. And then all of these are the experimental group. All right, next question. Do you think that doing just 1 trial of each is enough? And the answer to that is probably no. Again, the more trials you do, the more evidence you have, and something that's fluky can't happen or cause you to believe something that isn't true. What would a good title be? Well, if our independent variable is the amount of antifreeze and the dependent variable is the time to freeze, then a good title would be something like how the amount of antifreeze affects the time to freeze. Okay, I've got my independent variable, the amount of antifreeze, and the time to freeze is my dependent variable. Good hypothesis. Now I want to say what I think is going to happen. I'm going to say if I use 3 tablespoons of antifreeze, then the water will freeze the slowest. Okay, if then statement, I specifically say which independent variable I want to change, or how it's going to change, and then how will that affect the dependent variable, and I say that that will be the one that's the slowest. All right, then I said make a data table for the data in this graph. I should have said in this paragraph. Okay, so if I make a data table, I've got a column here for amount of antifreeze, and I have 0, 1, 2, 3, 4 tablespoons of antifreeze. And then the next thing is time to freeze. And I'm going to have to go back to my paragraph. Excuse me. And the paragraph says, for bucket 1, the water freezes in 55 minutes. Bucket 2, it's 110. Bucket 3, it's 220. 440, and 880. All right. And then if I make a graph of that, my independent variable goes on the bottom. That is the amount of antifreeze. Side is time to freeze. A good scale here, 0 to 4. So that's going to be 0, 1, 2, 3, 4. And then this one's going to go from 0, well, let's say 0 to 1,000. Okay, so I'm going to put 1,000 up here. And so that's going to be 500. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. So 100, 200, 300, 400. All right, and so 0, 55, that's about right there. 1, 110, that's about right there. 2, 220. 3, 440. And 4, 880. In this graph, makes a nice smooth curve. So that's what we would say is it's probably like a, well, I'm doubling every time. So geometric series. Anyway, looks nice. Okay, so that is that, what that graph would look like. Okay, so those are kind of terms and things you got to remember for when you are doing experiments. All right, the other thing you're going to have to know is what are the, how to do the dimensional analysis. And so I'm going to run through some different problems here. Remember that these all take the general form of set your unknown equal to your known value, and then there's only going to be one conversion factor for each of these. All right, so first one, if 16 tablespoons equals 1 cup, how many tablespoons are in 4.3 cups? All right, so how many tablespoons? That is my unknown. So I'm going to say x tablespoons. My known value in this one is 4.3 cups. So I'm going to say x tablespoons equals 4.3 cups. And now I need a conversion factor. Okay, Here's my conversion factor. 16 tablespoons equals 1 cup. I know one of those goes on top of that fraction, the other one goes on the bottom. And so I look to my known term, and what are the units here? They're cups, and they're on top. And so cups here have to go on the bottom. So 1 cup goes right here, and then that means 16 tablespoons. And that goes here, and that goes there. Okay, so cups cancel out cups, and I go 4.3 times 16, and I get 68.8. 68.8 tablespoons. All right, next one. There are 1,000 meters in 1 kilometer. How many kilometers are in 1,607 meters? Okay, so again, if I'm reading at the beginning here, I say there are 1,000 meters in 1 kilometer. Neither of those is an unknown value. And what does this mean? It means that they're equal to each other. So those are the two things that are going to go in my conversion factor, because they're equal to each other. How many kilometers? That's my unknown value. And then my known value is the 1,607 meters. So my unknown, x kilometers, equals my known value of 1,607 meters. And then my equality here, those are the two items that'll go in the conversion factor. If I have meters on top, meters have to go on the bottom, and I have 1,000 meters in 1 kilometer. So I cancel out meters because they're same. And then multiply 1,607 times 1 kilometers. Kilometers come over 2. Divide that by 1,000 because that's on the bottom. 1,607 divided by 1,000 is 1.607 kilometers. All right, if someone weighs 240 pounds, how many kilograms are they? Okay, so this is my known value. How many kilograms is my unknown? And then this is my equality, so that's my conversion factor right there. So I go x kilograms equals 240 pounds. 2.2 pounds goes on the bottom, and 1 kilogram goes on top. So pounds cancel pounds. So here I'm going to go 240 divided by 2.2. That's 109.1. Again, I multiplied across the top to get 240 kilograms over 2.2. There's a 1 right here. Multiply those across, and that's how I get that. And then I get 109.1 kilograms. All right, how many seconds are in 1 hour? All right, so how many seconds is an unknown? 1 hour is my known. I didn't give you any conversion factor, but I think you know how to change time. Actually, this turns out to be a 2-stepper or a 1-stepper. I'm going to do it as 1 step just because I remember what it is, but you can do it in 2. So x seconds equals 1 hour. And I know that 1 hour is the same as 3,600 seconds. So hours cancel hours, and I get 3,600 seconds. Okay, so I kind of knew the answer to that. What if I didn't? What if I said x seconds equals 1 hour, and I go 1 hour is the same as 60 minutes, because everybody, I hope, knows that. And then 1 minute equals 60 seconds. And I go 60 times 1 is 3,600 seconds. So, same answer. I've just done this a long time, so I know that there are 3,600 seconds in an hour. Okay, 2 more. If you have 14.1 centimeters, so that's a known, how many millimeters, that's an unknown, do you have? Oh, this is actually the last one. Now, I can do this in 2 different ways. I'll do it the regular way first. I know that there are 100 centimeters in 1 meter. I know there are 1,000 millimeters in 1 meter. So I might have to do this as a two-step problem. So I'm going to go, I'll do it down here. So I'm going to go x millimeters equals 14.1 centimeters. And I want to get rid of centimeters. So 100 centimeters equals 1 meter. But that gives me meters. I want to know how many millimeters I have, so I'm going to use another conversion factor. 1 meter equals 1,000 millimeters. Just make a bunch of squiggles for 2 m's. And so here I get 14.1 times 1,000. So that's going to be 14,100 millimeters. But it's all divided by 100. And so that's going to ultimately be 141 millimeters. Now, if I'm changing metric to metric, there is an easier way. So, if I have 14.1 centimeters, I write 14.1 there, but here I've listed out all of the metric prefixes. Kilo, hecto, deca, unit, which can be a plain old meter, liter, or gram, deci, centa, and milli. So centa goes right here. How many millimeters do I have? I want to get my decimal point from here to there. So I'm going to move it over 1 spot, and now that decimal point comes after the 1. So that's 141 millimeters. Okay, and look at that. Same. Okay, so when you do metric to metric, you can just slide your decimal around. You don't have to do any of this stuff up here. All right, that is all I've got. Study well, get a good night's sleep, and I will see you when you take your test.